If we are given initial concentrations of reactants and products for an equilibrium reaction, we can test whether we are at equilibrium by writing what is called the reaction quotient. Q sub C is defined as the concentration of C to the C power initially, D to the D power initially, divided by the concentration of A to the A power initially, and B to the B power initially. If QC is greater than Kc, the system proceeds from right to left to reach equilibrium. If QC equals Kc, the system is at equilibrium. If QC is less than Kc, the system proceeds from left to right to reach equilibrium. Let's turn our attention now to calculating equilibrium concentrations. First thing to do is to express the equilibrium concentrations of all species in terms of the initial concentrations and a single unknown, x, which represents the change in concentration. We then write the equilibrium constant expression in terms of the equilibrium concentrations. Knowing the value of the equilibrium constant, we can solve for x. Having solved for x, we have to calculate the equilibrium concentration of all species. Let's take an example. At 1280 degrees C, the equilibrium constant K sub C for the reaction Br2 in equilibrium with 2Br is 1.1 times 10 to the minus 3. If the initial concentration of Br2 is equal to 0.063 molar and the concentration of Br is 0.012 molar, calculate the concentration of these species at equilibrium. Let x be the change in the concentration of Br2. Here is the equilibrium again. Initially, we have 0.063 molar Br2 and 0.012 molar Br. We're going to say the change is minus x, y minus because Br2 is disappearing, and a positive 2x for Br. Positive because it's appearing, and 2 because there's a coefficient of 2 in front of Br. At equilibrium, we sum up the two lines, 0.063 minus x and 0.012 plus 2x. This table is called ICE, or the ICE table. We now substitute in the values. For Br, we put in 0.012 plus 2x, and remember we had to square that. In the denominator, 0.063 minus x, setting that equal to the equilibrium constant 1.1 times 10 to the minus 3. This is going to be a quadratic equation. Cross-multiplying 4x squared plus 0.048x plus 0.000144 equals 0.0000693 minus 0.0011x. Simplifying and setting equal to 0, we have the following. This is the quadratic form, and we're going to use the quadratic equation minus b plus minus the square root of b squared minus 4ac divided by 2a. If you need help reviewing that, remember there's mathematical appendix in your textbook. B, A, and C represent the coefficients. Substituting in, we get two values. Remember, when you solve a quadratic, you always get two values. Negative 0.0105, and x can also be negative 0.00178. Which is correct? Going back to the table and what it represents, remember we have to subtract x from 0.063 to get the concentration of Br2, and we have to add 2x to 0.012. If we start with Br and add 2x 2 times a negative 0.0105, the answer comes out to be a negative 0.009 molar. You can't have a negative molarity, so this answer does not make sense. Using negative 0.00178, we evaluate that by adding it 2 times that to 0.012, and we arrive at 0.00844 molar. For Br2, we take the negative 0.00178 and subtract it to 0.062, and we come out with 0.0648. We will do many of these problems in class together. Le Chatelier's principle. What happens to an equilibrium if we change things by adding a reactant or a concentration, or removing it, or changing temperature? Let's start with change in concentration. Here's an equilibrium between N2H2 and NH3. Suppose we add NH3. The equilibrium is going to shift to the left to offset the stress. Let's look at this some more. Using this hypothetical reaction, what happens if we increase the concentration of products? The equilibrium will shift to the left. If we decrease the concentration of the products, the equilibrium will be reattained by shifting to the right. If we increase the concentration of reactants, the shift in equilibrium is to the right. And if we decrease the concentration of the reactants, the shift in equilibrium is to the left. How about volume and pressure changes? If we increase the pressure, the shift in equilibrium will be to the side with the fewest moles of gas. If we decrease the pressure, the equilibrium will shift to the side with the most moles of gas. If we increase the volume, the shift is to the side with most moles of gas. And if we decrease the volume, the equilibrium shifts to the side with the fewest moles of gas. Temperature. How do changes in temperature affect equilibrium? If we increase the temperature, the K for an exothermic reaction will decrease. The K for an endothermic reaction will increase. That is, an increase in temperature favors an endothermic reaction. A decrease in temperature, K will increase for an exothermic reaction, and K will decrease for an endothermic reaction. So decreasing the temperature favors an exothermic reaction. Finally, adding a catalyst. Adding a catalyst does not change the value of the equilibrium constant. It does not shift the position of an equilibrium system, and the system will simply reach equilibrium sooner. Here we see the effect of adding a catalyst. The catalyst lowers the activation energy for both the forward and reverse reaction. It does not change the equilibrium constant or shift the equilibrium. Here's a table summarizing Le Chatelier's principle. You can also find this table in your text.